Hello students, welcome to this session. Now let's continue the 2-in-1 series in which the last session we have started the concept of semaphore and in which we understand the definitions as well as the counting semaphore we have discussed, the implementation part also we have seen. So now we will see the binary semaphore, how binary semaphore will work out, we will observe it. So binary semaphore takes two things 0, 1 only, it takes the two values, where counting semaphore is taking minus infinity to the plus infinity the values is the implementation structure and how to use in a user mode applications, that part we have covered in a last session. So try to cover it like try to watch the video the semaphore part 1 ma. So looking at the binary semaphore, it takes only two integer values, that is 0, 1. So looking at the implementation, the structure, the basically I am using the structures I am using the struct. So binary semaphore, B semaphore means what? So binary semaphore. The structure members are understand, it takes only two values, so we can enumerate. So I can use a enumerator data type, so values. So this is taking what? It is only taking the 0, 1, right? So I am defining this one. The followed by L is a Q, right? Q type, right? So Q type, L is a Q type. What this L contains? Even when in case of counting semaphore also we have seen, L is a data structure, Q data structure, which contain the list of blocked processes. So this processes got blocked while performing the down operation unsuccessfully. This is the structure members. There are two important structure members are the value of, this is define the current value of semaphore, this defining the, so how many processes got blocked. So during performing while performing the down operation with unsuccessfully. In a last session also we have seen, so understanding the what is a successful operation and unsuccessful operation. So before looking at the video number 2, this part 2, so kindly watch the semaphore part 1 where I discuss clearly understanding the semaphores and the counting semaphore. Let's continue this part. So in the application, suppose in a user mode of application, understand user mode of application where shared code is there, and where that's we call critical section. When you want to ensure, like when you want to protect the critical section, like by allowing only one process to use the critical section, so we can use a semaphore operation to control it. So this initialization of the binary semaphore, understand. So the structure name is what? Binary semaphore, right? So binary semaphore. For this, the variable I am declaring what? S. So initializing this S dot value, so assigning what? 1 only. So you understand the value which can take either 0 or 1. So 1 I am assigning now. So once you declare, like implement the declaration and assignment is over, the users comes like suppose here is a critical section. This is a critical section. So this critical section should be ensured like enclosed by various semaphore operations. So I may using like a down operation on this semaphore variable S. The followed by I may using what? Up operation on S. The followed by set of statements like this. So this upside and downside is a non-critical part, where the critical section is there, this must be enclosed by the semaphore operation. And also we have noticed, we have understand, it is not compulsion, the down operation, there are semaphore operations are 2, down and up, and it is not compulsion, you should start with the down operation. You can start with up operation. You can have even set of multiple the semaphore operations also can placed. That completely depends on the requirement of the application, but usage will be like this. So now, so look at the structure, like what architecture. What is the architecture? The architecture has entry section, okay, entry section where raise condition also present. Let's suppose there are 3 process raising to access the critical section. So like critical section. So in this entry section, we are placing what? We are placing binary semaphore operations. You can place it to up operation or down operation. Let's say I am placed what? So down of a suppose assumption, and followed by here is a critical section where processes will enter and to access the shared code here. Once usage is over, this critical section usage is over, it leaves from the critical section that we called exit section. In exit section again I can use operation, semaphore operation, either you can use up operation or you can use down operation, that is completely based on your requirement. So this is in application you can use it like this is structure or the mechanism or architecture, you can see how the entry followed by exit, in between what critical section is there. Let us take the case study to understand how this binary semaphore can work. So that we will observe with the example. Okay, the same structure I am trying to take here. Okay, we have a entry section, right? Entry section, entry section, entry section. Here is what? Critical section, critical section, critical section. Okay, critical section. Then the exit section is there. Exit section. Okay, exit section. Okay. In the entry section, I am placing the down operation on S. Okay. Exit section, I am placing what? Up operation on S here. Now race condition is present, P1 and P2. Let's take P3. Three processes are raising to or trying to access the critical section assumption. Okay. Now this is scenario. So we are taking the concurrent environment. So ready queue presents, ready queue has three processes where process P1, process P2 and process P3 is there. Now as an example I would taken like a down first operation, then followed by up operation I am using. And also I am saying that this semaphore value I initialized as one assumption. We initialize one, because either 0 or 1 can we have. So I initialized 1. Then let us understand the sequence of steps we carried out while this process trying to access the critical section here. Let us take at time t0, different scheduling algorithm might be working, like one of the scheduling algorithms we used and to schedule these processes. So like suppose process P1 schedule assumption, process P1 schedule. What process P1 has to do? So maybe initially spending the non-critical section work which is not required to use a shared code. Now suddenly it is required to use a critical section, then critical section is enclosed by semaphore operation. So now down on S has to perform before accessing the critical section, right? So we also understand the down operation can be also like represent like the P of S. Either you can write it down of S or P of S or weight of S, all three are same only, right? So what is this P of S? Down of S. Down of S nothing but decrement the current semaphore value by 1 only. So now after executing this statement, S value initially 1, this becomes what? 0, right? S value becomes 0. S value becomes 0 now. So when like S value, so I am writing when, so one important point you should notice here. Okay. So S value was what? 1. Okay. So now S is going to be what? Changing what? 0, right? S is changed to 0 when I perform down of S. In binary semaphore, please understand, when S value 1 is changed to 0 is a successful operation. Successful operation. So once operation is successful, what we know? So this can enter into critical section. So now writing here. So process P1 has enter into critical section, critical section. The critical section has set of shared code, right? Set of shared code like this, no? Critical set of instruction will be there. It is running, started executing. During this its execution, preemption can happen because since it is in a user mode statement, but shared code is there. So during this execution, suppose preemption occurred. So I am showing like this point, PR means preemption occurred. The preemption nothing but process P1 has to leave the CPU state and other process need to be scheduled. So let's take a time T4, at time T4. So process P2 has scheduled now. P1 came back to ready queue and P2 scheduled into CPU state. So P2 might be running something code, then again it is required to run the shared code, trying to access now critical section. So critical section and before what is the down operation. So now process P2 also perform P of S, P of S. So currently S value how much? Currently S value is 0 now. So now 0 down. So what is the meaning we understand? Down operation. Down means it decrement the current semaphore value by 1. But in a binary semaphore I do not have -1s, right? So when the current value of semaphore is 0, if I perform the down operation, down on 0 is 0 only. It is changing from, So 0 to 0 only, no changes. But this was a successful operation, please understand. This is successful operation. This becomes an unsuccessful operation. This we have to notice now. When the binary semaphore value changing from 0 to 0 is unsuccessful operation, changing from 1 to 0 is successful operation. The successful operation results is process has to enter into critical section to use. Unsuccessful operation results into you have to block it. So now this process need to be block. You have to block it. Okay, you have to block. So blocked process P2 blocked. Let me also maintain here. Here trying to maintain S dot L. Okay, S dot L is a Q, right? S is a structure member, like where what the semaphore, and L is a Q, right? Q. So I am using the Q data structures to maintain the list of what blocked processes. The process P2 got blocked. Process P2 got blocked. So also you should notice now in this moment, it is also ensuring what mutual exclusion or not. Why? Because when process P1 was in critical section, not completed, it was holding the critical section, came out of the CPU, same critical section process 2 want to enter into that one. So not able to enter, it got blocked. Yes, I can ensure. The semaphore is ensuring the mutual exclusion. Yes, I discussed told in the in the beginning, like before session. It is a practical implementable algorithm. It is ensuring, it is satisfying all the synchronization mechanism requirements. One of the requirement is what satisfying the mutual exclusion. It is satisfying the mutual exclusion, not allowing to enter the critical section. Yes. So it is got blocked. Now ready queue is having only process P1 and P3. Let's also continue. So now at time T8 assumption, process P3 try to enter the critical section. Suppose it is directly trying to enter the critical section, it is also perform P of S now. What is S value currently? S value 0. Now down on 0 means what? Down on 0 changes to what? 0 only. So S becomes 0. So this operation we called what? Unsuccessful operation. Unsuccessful operation. Results in what? We should block it. We should block. So now process P3 also got blocked. So process P3 also blocked here. So now process P3 got blocked because that's the only reason. P1 was in critical section. Now we are not allowing ensuring the mutual exclusion here. So now left over with the ready queue is what? P1 only. After some time, let's say time T12 I am taking, process P1 got a chance. So where is the process P1? P1 was in critical section. It was running some set of instruction, got preempted, right? So now it is completing the rest of the code. Process P1 complete the rest of the code of the critical section. Now try to leave what? Try to leave the up operation. Exit means you should perform the up operation. If you perform up of S, you have to perform up of S. So what is up operation defines now? What we observed from the counting semaphore up operations, we have implemented the up operation also. You should decrement, right? Sorry, you should increment the what? Semaphore value, right? So so what we have studied in case of counting semaphore case, first increment, then if any blocked process is there, you should wake up. That we understand. So let's do it again, same thing, right? Yes or no? Now see, so I'm just showing the up operation, right? So now process P1, this one will, right? Process, so P1 only doing, right? At time T12, like 212, P1 was doing. So this P1 things only, it is performing what? Up operation, right? Upon S. So what should I do now? Up operation. Should I increment? So as per the counting semaphore, what we did? First we incremented the semaphore value. We tested this or semaphore value, and if it is still negative, we have to wake up the process. We have seen, right? Suppose if I increment right now, what is S value currently? 0. 0 if I increment what becomes 1. Is it desirable operation to incrementing the the semaphore value in this moment? You pause the video, think. If I increment now, S becomes 0, that means if any new process, can it try to enter the critical section? Will it get succeed or not? Any moment of time you see, as per this model, if S equal to 1, any new process can try to perform the down operation or not. If it is perform the down operation, S equal to 1 down 0 successful, the process is going to be enter the critical section. But there are 2 processes already blocked, right? So if I allow new process, this process is going to be starvating, correct or not? It gets starvated because other process will come. So nobody going to wake up this processes, right? So it is not desirable operation. immediately incrementing. The first operation under the up operation, we have to do it, you first you test it whether Q is empty or not, whether Q is empty or not. How to know like how many processes are blocked here? Please understand, in case of counting semaphore, by looking the current value of semaphore, we can understand those many processes may be successful or blocked processes. If for example, S equal to -2, there are 2 blocked processes are there. By looking at the S value, we can understand these many processes are blocked. But in case of binary semaphore, it is not possible, because so this Q is not stored anywhere. So currently S value is 0 only. If whether the Q is empty, if the process in critical section, if there are n number of process Q, still S value is 0 only, correct or not? So by reading at the S value, we will not able to understand whether the process are blocked or not. Hence, we need to check the Q, like now you understand. So first operation, S dot L is a Q, is empty, we should check it like this. Is it empty? Like we should check the condition. If it is empty, so I am writing no. If it is suppose not empty, no assumption, answer is no. Then what should I do? You should wake up, okay, wake up the process, wake up the process. As per this example, which process I should wake up? Should I wake up P2 or P3? Pause the video thing. Should I wake up P2 or P3? You understand? So among these 2 processes, P2 got blocked first. So you should wake up the P2 only, because we implemented the FIFO, I said first in first out. If you are using FIFO to like storing the maintain the list of blocked process, we can say strong semaphore, we can say. Other than FIFO data structure, if you use it, that becomes what, weak semaphore. There is a starvation possible, and bounded weight may not be guaranteed if I not follow FIFO data structure to maintain the list of blocked processes. Hence, I should wake up what process? P2 only. So process P2 I should wake up. Okay, getting my point. So now what is second point? Second point, if it is empty, S dot, okay, S dot L is suppose like second point I am taking directly. Yes, okay, if it is yes, then you should increment it. You should increment, okay, increment what? Yes value. This you have to do. But as per this example, so S dot L is not empty. No, means what? Not empty. Some process other. You should wake up this one. So I should not perform this operation. So I'm generalizing. Up operation has to do two activity you have to perform. First you test it. If the Q is not empty, wake up the process. Else, if the Q is empty, make it what? So make it what? Increment this one. So this is what? Else part I am taking. Else part. Okay. So else part not going to be executed. So now we wake up the what? Process P2. Now let's take, I am continuing this execution. At time suppose, at 16 assumption, so now we wake up the process. So now my question to all of you, just pause the video thing. So process P1 completed the critical section work, performed the up operation. Now it is wake up the P2. Where P2 will come? Does it execute any instruction or does it directly enter in the critical section? So that you have to notice. Process P2, when it was running, during the down operation, it got blocked. So now it will run the next instruction, next down follow next instruction or critical section only. At time T16, I am writing process P2 will enter into what? Critical section. Okay, critical section. So once critical section work over, it is also runs out up operation upon S. So what this up operation has to do? Up operation of S. Okay, S value currently 0 only, right? Currently 0. First you test first condition. So does S dot L, so does S dot L is empty? You should run this one. Okay. So answer is what? Answer is as of now, no. Still process are there. We should wake up the process. Wake up the process. Which one? So process P3 left over. So process P3 should wake up. Process P3 we should wake up, right? So now let's take at time T20. At time T20. So process P3 came to where? Directly it will come to critical section. The critical section job completes. Once this is done, it is also perform what? Upon S. Now upon S. What is step number 1? S dot L is empty. Is empty. This question answer is what? What is the answer right now? Yes, it is empty. So then empty means what should I do? Increment. So increment S value. So right now S value is 0. So I am incrementing to 1. So does means all the process, blocked process got successfully executed. Now you can make S equal to 1. If new process anybody tries, so definitely it get this succeeded. So this way you understand. So this analysis part, this analysis part you understand, it is guarantee the mutual exclusion. So now how to test whether it is satisfying the progress condition or bounded weight condition. So how to test that one? Let's observe in this case only. So mutual exclusion is guaranteed. How to check the progression? So progression you understand, any moment, suppose initial S equal to 1. When critical section is free, if any process tried, no other process should not stop other interested process who are willing to enter the critical section, right? If S equal to 1, P1, P2, P3 suppose are raising, but P1 is not interested to enter the critical section. If it is not interested to enter the critical section, it won't perform the down of S. It won't perform the down of. Any process perform the down of S operation, meaning it is interested to use the critical section. There is no point I perform the down operation, then I am saying that I will not run any instruction. Means when you perform the down of S, nothing but you are entering, like you enter in critical section. So then you are using the critical section only. If any process not interested to enter the critical section, it won't perform the down operation. Hence, so nobody stopping other process who are willing to enter the critical section. So I can declare yes, progression requirement also satisfying, because when S equal to 1, any process can try. So third condition, so does it guarantee the bounded weight condition or not? Since we are maintaining the FIFO data structure to loading or like to maintain what list of blocked process, we are using FIFO. So definitely guarantee the bounded weight only. How to understand, sir? How to understand? You can suppose you see the scenario. See the scenario. Suppose P1 was first started assumption. If perform the down of S equal to 1, it became S equal to 0. Successful operation. P1 entered the critical section. Okay. So during its execution, preemption occurred, and P2 tried. So S value 0, 0 down 0, unsuccessful. It got blocked, right? Blocked. Now P1 where P1 is in ready queue and P2 got blocked, and P3 also got blocked. Assumption. After some time P1 came, it completed critical section work and performing up operation assumption. What is up operation? What is the up operation now? Up operation is what? So I am checking queue is empty or not. Not empty. So just we are wake upping P2. Okay. Assumption. So like up operation is the, like you understand, up operation, during up operation time preemption will not happen, ma'am. During up operation time preemption will not happen. Okay. So suppose I wake up assumption. Process P2 wake up. So now suppose example, if I schedule only P1 only assumption, try, suppose P1 only tried again, it's not possible, again tried assumption. Will it able to enter or not, we'll see now. Suppose instead of P2 entering, P1 tried again, because already critical section work executed, P1 if you tried, down on S, what is S value currently? After performing up operation on S by process P1, still S value 0. Then after that, again if you retried, perform the down of S, S value 0, 0 down 0, what happened? Blocked, P1 going to be blocked. So there is no chances P1 will enter. So before completion of P2 and P3, hence definitely is guaranteed what? Bounded weight requirement. So now the major synchronization mechanism requirements are satisfied by this semaphore, hence definitely we can implement practical cases. One more important point we should notice, the binary semaphore is a special cases, like binaries have special cases of the counting semaphore. So we can implement binary semaphore, we can implement through what? Counting semaphore or not? Yes, sometimes the statement can give which of the following statements are true. Statement 1, binary semaphore can be implemented through counting semaphore. Yes, possible, because when I control, so taking only from counting semaphore, take 0, 1, that becomes binary semaphore. Statement 2, so binary counting semaphore can be implemented by using binary semaphore. So what is statement 2? Counting semaphore can be implemented through binary semaphore. It's not possible, because counting semaphore require lot of values, but in binary semaphore only we have 0, 1, we cannot implement. Only statement 1 is a true statement, we can understand. So these are the important point. I hope you understand. So conclusion is what? What is the conclusion? Binary semaphore, so guaranteeing the mutual exclusion and progress requirement as well as bounded weight things is guaranteed. Some observation we can make it. So we can So put the node point wise, we can observe it. Okay, the first point. Okay, first point. Take the scenario, binary semaphore value, S value, suppose 0 is there. So initially binary semaphore, I am taking binary semaphore S value, initially 0 is there. The first one you understand, I am performing, suppose example, so down up operation, okay, down on S if I perform down on S, what happens? What is S value will get? What is S value? S equal to will get still what? 0 only. What is the status of the operation? Status of the operation is successful or unsuccessful. Initially S value is 0. When I perform down on S still 0. So this we called unsuccessful operation. Unsuccessful operation. This information will help you to solve the problems. You can notice when binary semaphore initially is 0, after down operation 0 only, naming what? Unsuccessful operation. This is point number 1. So point number 2, understand. S equal to 0, binary semaphore S equal to 0. So I perform the operation down on, up on S I am performing. What is S value? S value. Initially binary semaphore value S equal to 0, I perform S upon S. So this becomes 1. The status, so status will be successful operation, that should understand. Okay, if the value is 0, you are making up, so you are making incrementing means 1, so the successful operation you can tell. So there is no point unsuccessful operation while performing the up operation successful only. This is note point number 2, this you have to notice. So point number 3, so binary semaphore value S equal to 1 is there, S equal to 1, okay, S equal to 1 initially. So I perform the down of S, P of S means down of S. The first thing you should note it, S value becomes 0, 1 down, 0. Then second, what is status of the operation? The status of the operation is again successful operation only, successful operation, this you have to notice. So point number 4, binary semaphore S equal to 1, so I perform the V of S operation, up operation. So what is S value becomes? S value still becomes 1 only. The second one, the status of the operation, again successful operation only. I repeat my point, there is no point unsuccessful operation while performing the up operation. So these are the 4 important points we can notice from the binary semaphore. So I hope you, so those who watch the part 1, semaphore of part 1 and this thing, so definitely you will understand the concept of the semaphore and its implementation in terms of counting semaphore as well as the binary semaphore. So let's see some questions, what type of question they can ask in a gate paper, we'll see. Consider non-negative. Sorry, before this answering this question, we can try one more question also, like we can see. Suppose, so I am taking the scenario. So initially binary semaphore value, S equal to suppose 1 assumption, okay. And the following operations are carried out assumption. Following operations are carried out. On this semaphore. Let's take, I am taking scenario 10P operations, 6V operations, 3P operations and 4V operations, comma, and 8P operations are carried out assumption. And question number 1 they can ask what is the value of S? Value of S after this one. And question number 2, what is the value of this? Question number 2, number of blocked processes after performing these operations. Number of blocked processes, how many? This type of question that can be framed here. Let's understand. Initially S value how much? 1. Okay. What is the first operation? 10P down operation. If I perform one operation, this becomes 0 or not? It is successful operation or not? Remaining 9 operations are going to be what? Blocked. So still this value will be 0. Let me maintain S dot L is a Q. S dot L is a Q. Okay, Q. Out of 10 P operation, 1 operation successful, remaining 9 processes blocked. So I maintain 9 blocked here, 9 blocked processes. The followed by, understand, followed by 6 V operations. What is 6 V operations? V means wake up. So I have to wake up 6 process. Still 3 process blocked only. In this moment, if I ask you what is the value of semaphore, still 0 only. Still 0 only. Please understand. So this part, this over, this over. 3 down operation. Right now S value is 0. Already 3 blocked process available. We are performing 3 down operation. So this becomes what? 6. Am I right? 6 or not? This value becomes 6 because these 3 processes also get blocked. This done. Then 4 V operations. So out of 6 we have to wake up 4. So remaining 2 will be blocked here. Correct or not? Then 8 down operations. So what happens? Now this 10, 8 also becomes what? Blocked. So total the value 10. Meaning what? There are 10 blocked process will be there. So what is S value will be? S value will be 0 only. So one thing you should notice, all of you. If there is a blocked process, please, if there is a process in critical section, if there is a process in critical section, or if there are process in blocked state, the binary semaphore value must be 0. This is important point now. Okay. Suppose example, one more statement if I give it. Binary semaphore value 0. Currently binary semaphore value 0. Can we guarantee that definitely there is a process in critical section or there are process in blocked state? So this statement is going to be wrong. We do not know. I mentioned clearly, initial value of binary semaphore is not necessarily always 1. It can be defined with a 0. It can be start with 0 also based on requirement only, based on requirement. But any moment of time, if there is a process in critical section or if there are process in blocked state, definitely value of binary semaphore must be 0. This is I can conclude the statement. So I hope you understand. Let's move another question. Look, consider non-negative counting semaphore S given and the operation P of S decrement the S and V of S increment S. During an execution, 20 P operations performed and 12 V operations are issued in the some order. The largest initial value of S for which at least one P of operation will remain blocked is dash. So 2016 paper for in a set number 2, 2 marks question they have framed it. So what they are asking? The largest initial value of S for which at least one blocked process should be present, and also one important non-negative counting semaphore. Non-negative counting semaphore starts from where? 0, right? Yes or no? The minimum value of counting semaphore, if I want to say, can I say 0 or not? 0 is the minimum. But they are asking largest value. I don't know what is the largest value. Let's understand. So non-negative start from 0. Suppose if I take 0. So 20 down operation means what? It become minus 20. And 12 V operation nothing but it becomes minus 8. Okay. So minus 8 defines there are 8 blocked process in the system, correct or not? So if there are 8 nothing but they said at least one blocked. So 8 condition is satisfied. Requirement is satisfied as per the question, but they have asked what? Largest value. If they could have asked what is the smallest value of S, initial value of S, so at least one block process is there, we could have taken what? S value what? 0. But they are asking largest value. So what is the largest value possible? So I should think 8 minus 8. 8 block processor. Suppose let's take, if I take S equal to 8 assumption, what happens? S equal to 8. So now 20 down operation means it become minus 12. 12 up operation, this becomes 0. S equal to 0 and counting semaphore indicates no blocked process. But they are asking what? At least one should be there now. It is not meeting my requirement. So then S value must be what? 7 or not? You take 7. 20 down operation, this becomes minus 13. 12 up operation, this becomes minus 1, right? So minus 1 indicate there is a one blocked process. Yes. So now S equal to 7 only will get one blocked process. If I take S equal to 8, condition is not satisfied. So S equal to 7 becomes the largest value, you can say. Sir, how you check this 8? So my understanding S equal to 0, I tried for S equal to 1. Then we will get some observation, this becomes 7. Okay, this is reducing, let's go with S equal to 8. this becomes 0, is not satisfying. So definitely S equal to 7, this is going to satisfy the requirement. So this way we should understand. So this type of questions we can expect in the gate paper. Okay. Now, so just I want to discuss like what are the practical applications? What are the practical applications of semaphore? There are 3 problems we have, like there are 3 problems we consider as a classical IPC problem, inter-process communication problem, means where actually we can see problems in IPC environment. So there are many problems. So 3 we can define as the best examples for defining, yes, where you can see IPC like inter-process communication environment, so we are facing what? Inconsistency, data inconsistency. So such problems are, one is producer-consumer problem, reader-writer problem, dining-philosopher problem. So let's understand how semaphore is going to be implement these problems, how semaphore operations are going to ensure the consistency in this application, in this problem. So I'll be discussing. The first I will focus, so producer-consumer problem. So you can put the heading producer-consumer problem. Is also known to be bounded buffer problem. Producer-consumer problem is also known to be bounded buffer problem. I hope you might have studied producer-consumer problem. If not studied, no problem. Let me give first the problem statement. Let's understand the problem statement of the producer-consumer problem. Then we can see semaphore-based solution for the producer-consumer problem. Understand clearly. So producer-consumer problem. So you understand the producer is one process, consumer is another process. So producer is the one process, please understand. The producer is what? One process, and consumer is what? Another process. Consumer is what? Another process. There are 2 processes are there, producer, consumer. Okay. So both are sharing a common buffer. Both are sharing the shared resource, you can say, the common buffer. Let me define this as 100 slots are there, 100 slots like this. Slot 0, slot 1, slot 2, slot 3, slot 4, like this slot. 0, 1, 2, 3, 4, 5, like 99. Okay, buffer size 99. Total size 100. So now what is the problem statement here? The producer is a process is producing or creating an information. So that is placed in the buffer. And consumer is another process which takes the information from the buffer and consume it. So how to understand this producer-consumer problem? You can treat it in the compiler phases. You might have studied various phases of compiler design, lexical analysis and syntax analysis, parser and semantic analysis like this. You treat like a lexical analyzer and generating the tokens which are requested by the syntax analyzer. So continuously generate these tokens. The tokens are placed in buffer which are consumed by the syntax analyzer. So these 2 are continuous process, keep on produce and consume it. There would be, please understand, practical cases, there would be n number of producers, n number of consumers also. But taking the consideration, one producer and consumer problem, and finite buffer, bounded buffer problem is what? Buffer size is limited here. You should correlate this process into lexical analyzer and syntax analyzer point of view, you can say. Now come to the problem statement. What I said, you just keep on produce information, and this information consumed by another process, that consumer. The both are using some local variable called in, which is in slice 0, and it is using the out variable in slice 0. This in is indicate, so next to free slot in the buffer where I can place information. I will produce information and place in the buffer. The out variable in consumer defines that the next item to be consumed from this location. If it is pointed to 0, from 0 location I should consume next. It is pointed to 0 means what? In a 0 location I have to place the information. Right now buffer is empty. So now if I produce information at this location I have to place it. That is the definition of these 2 variables. And these 2 are continuous process, keep on producing. But the problem, the original problem, if I see, there was like an inconsistency between this, So you should understand, go back and understand the problem. So implementation, there is an inconsistency in this system. Why? Because both are sharing common thing. It is producing and consuming, right? So when it's producing, it is maybe increment in the information count. It is consuming, right? It is maybe decrement in the count information. During incrementation and decrementation, if these 2 processes allowed to perform this operation, So definitely creating one inconsistency. Hence we need some kind of synchronization mechanism. So to make it a consistency, yes, we are going to see through our semaphore based one. Okay. So now common buffer is this one, right? Common buffer this one. Now it has to maintain the sum, how many items are produced, it has to maintain how many items are consumed, like this. Okay. I will be using some variables here. I will be using some variables. Okay. Now look this. The first variable I would like to use what? Empty variable. Okay. Empty variable. Okay. Empty. Empty defining, like I am just making it n empty equal to n. Indicates empty, there are n empty slots. So I am defining, okay, empty, number of empty slots. Number of empty slots in the buffer. Okay. How many empty slots? As per the example, 100. 100 empty slots are there. Suppose if I place the information, empty slot will reduce or not? If I place 2 information assumption, 2 empty slot reduces like this. So this is related to the producer, the empty variable related to producer. So another variable I am using full value I am defining as 0, indicates number of full slots in the buffer. Okay. So what is a full? Example, right now full value is 0. Right now full value is 0 because there is no any information here. If I place is 10 items assumption, full equal to 10, empty becomes almost 90, total buffers 100. If I place 10 items here, full becomes what? 10, empty becomes what? 90. That's to understand. The full defines how many full slots available. So now this to our cooperating process. Producer get affected by the consumer when buffer is full. When buffer is full, you cannot place information, right? So producer get affected by the consumer when buffer is full. And consumer get affected by the producer when buffer is empty. So there are no any items to consume it. So I have to stop. I do not have work to fetch any items from the buffer when the buffer is empty. That's what cooperation. How you understand cooperation? So producer get affected by consumer and consumer get affected by the producer. That's what I understand. There's 2 important variables I'm using. Followed by I'll use what? Mutex. So mutex is the operating system resource to understand, and is trying to ensure the mutual exclusion between any 2 entities. Now to access this buffer, so because this is trying to place is trying to consume it, right? So now this is a critical section, understand? The critical section should be accessed, we should ensure mutual exclusion. One at a time should be accessed to ensure this mutual exclusion. Another variable I am trying to use, what? Mutex, which I am defining one, it ensures the mutual exclusion between producer and consumer. Okay. So these are the 3 important variables I am going to use, and apart from this one, local variables also will be there. Let's understand. I am trying to write the code. So try to write the code for producer consumer problem by using semaphore. So now I'll define for as defined, okay, size, buffer size. So as defined n. Let's take this n value 100 assumption. So I'm using a global variable called buffer into buffer, okay, buffer. What is the buffer size? N now, okay. So through which variables only process can access. As I mentioned, full variable counting semaphore, okay. So counting semaphore empty, okay, let me use. So counting semaphore I'm defining, semaphore empty, okay, counting semaphore empty. I am initializing what? N, okay, n, okay. This is the global variable only. So this indicates number of, okay, number of empty slots in the buffer, empty slot in the buffer. Another counting semaphore taking, another counting semaphore I'm taking full equal to what? 0. So number of full slots, number of full slots. So now taking binary semaphore mutex, okay. So mutex is a binary semaphore initialized to what? 1. It is going to ensures what? Mutual exclusion between producer process, another process what? Consumer, to access the buffer, These are the declarations things to understand. So now see, code for the producer you observe, code for the producer code understand, okay. Void, it is not returning anything, void producer, okay. producer, passing elements also wide like 0. Now see, okay. Local variable I am defining int, okay. We have to produce information, let us take information item, okay. Item naming as a P producer related, and local variable in equal to 0 I am defining. So now I say mention this continuous process, so while 1 true, statement 1, okay. To place the information in the buffer I should produce it. I am using a separate procedure call, so produce, okay, produce item, okay, I am passing the parameterized or item P. So this is separate produce procedure. When I call this function, it will jump to its routine and it will run and produce information, okay. What is second step now? So item is ready, please understand. The producer, when I want to place item in the buffer, I produced like I got, I have to place it, I have to place in the buffer. But also we should ensure, so I said this is a cooperating processes. Producer should stop placing information when buffer is what? When buffer is what? Full, correct or not? Full? Yes or no? You pause the video, think. When buffer is full, you cannot place it. So I must have some termination condition for this, right? So what I am trying to do here, so what is the variable maintained for the producer? Empty. What is empty? Empty slot. When empty slot becomes 0, what happens? Stop placing or not? When empty becomes 0, suppose empty becomes 0, what does mean? So no empty slot to place it. So when it becomes empty, you should be what? Stop placing what? You should block it. So now I am using semaphore operations, like you have to call what sleep function call, so that producer going to be sleep properly, then it is going to be wake up with the consumer when the buffer is empty. So for this, how to write the operation now? So I am going to do what? Down or through semaphore operations only, right? So down, okay. So down on empty I will perform. So down on empty. So what is happens? So understand now. Suppose keep on repeating, like suppose this code, some other code like other lines I also write it, means I am trying to produce n number of items, I fill the buffer assumption. Once the buffer is filled, empty value becomes 0. So again one more item may be produced, then I am running condition. Down on empty, empty becomes 0, 0 down minus 1. So produce should be sleep or not. So because when I call down on empty, unsuccessful operation should be blocked or not. That is what termination condition. Suppose if it is not empty, then I will go. Suppose empty value n, it is not empty, then second instruction I will run. What is second instruction I should place it? Placing item in the buffer only, right? Placing item in the buffer or not? But also notice, understand, buffer is a shared resource and shared between the producer and consumer. So now it should I should provide mutual exclusion. So I will use what? Down on mutex, okay. So down on mutex. Why mutex, sir? To ensure the mutual exclusion between what? Producer and consumer, like mutex. What is initial value mutex? 1. 1 down 0 successful. When I am using the buffer, consumer should not come. That is the reason I written. Okay. Fourth statement. Okay. I have to place simply buffer, right? So I have to place it like item I have to buffer. Okay. Buffer. Where to place? In variable giving where to place it. Buffer of in variable equal to. So item which you produce, right? Item P. I have to place it. I hope you understand this statement. Buffer is array. So with the index in is giving where to place it. The fifth statement. Okay. Once you place it, local variable I should increment. Why? Because I should point to next free slot. In equal to in plus 1. So I am making modulo n. Why, sir? Once 0 to 99 reaches, you should come back to 0, right? So 99. So in plus 1 modulo n. So this we done. Then. So now we place in information buffer. So I should wake up or not? Up. Up on what? Mutex plus, because other process consumer can use what buffer. The seventh statement, we perform down on empty, then empty reduce, full last increase or not. So now up of what? Up of full. So this you should understand code. Then I will be closing like this. This is a producer code. You pause the video properly and pause the video and properly observe the code for the producer. So I repeat my point. So his duty is response to place the item in the buffer. There must be some termination condition. So down on empty to access the code critical section we called. So mutual exclusion should be there. Mutex I perform. Then place item increment local variable. So I woke up making mutex equal to 1 so that consumer can come. And up means for full should increase. Initially full value 0 should increase. It should become 1. This is the code for the producer. Let me also see for code for the consumer. Code for the consumer. Code for the consumer. Void consumer. Void consumer. So void type. Okay. Then taking our local variables. So we have taken information from the buffer, right? So like taking item for consumer items I am writing. So local variable is what? Out. Through out variable only have to take it. Then this also repeating what? N number of times while 1. Okay. What's step number 1? Or step number 1? So consumer responsibility, you have to take the, like, go to the variable out and take the item from the buffer, correct or not? But I must know sometime, when the items are not present in the buffer, I should not, I do not have a right to access that buffer. So I hope you understand. So I must have some initial condition, like when buffer is empty, I should sleep, right? So now first I have to test the condition. What's testing condition? How to test this condition now? When buffer is empty, you have to sleep. Means what is buffer empty indicated by? Full or not? When full equal to 0, please understand. When full equal to 0 means what? Empty only, correctly. So directly I will perform what? Full. So down on full, sorry, down on full, because full is related to what? Consumer now, down on full. Suppose consumer only started first executing. Now if I perform down on full value already 0, 0 becomes -1. So consumer going to be blocked here. So that is sleeping. The second one, suppose full value something 10 is their assumption, 100 is there, full is 100 assumption, or full equal 1 is there, 1 down 0 successful. So here you should go for accessing what? Buffer. So as I mentioned, accessing the buffer should be what? Mutual exclusion, right? So down on mutex I will perform, right? Down on mutex I am performing here. Then the third step, you should take the item. Okay, name of the item is item C. Where to take? Buffer. Which index? So given by the out variable, correct or not? So once item you consumed it, so now you have to point to next item to be consumed, right? Out equal to out plus 1 modulo operation n. Then so once buffer access over, up mutex you should perform, Then sixth one, once item is consumed, okay, item is consumed, full should reduce, sorry, full is in, like what happens out of, so now down on full should decrease and empty should increase or not? I should perform what? Up of what? Empty now, up of empty operation need to be performed. The seventh step, just I am writing, consume it, consume, okay, consume item. So which item came? Item C came. This is a procedure to consume it like this, suppose. Okay. So this is a code for produce, this is a code for producer and consumer. Okay. So properly you can observe, and definitely this is going to ensure the consistency between the producer and consumer. No inconsistency will create during accessing or during communication. Semaphore are definitely solving all the things here. Okay. This observation. So you can check out also, you can trace out. So let me take the tracing part here. Okay, tracing part. So our analysis part, understand. So ready queue has, okay, two process, producer and consumer will be there. Suppose at time t0, if I schedule the producer, okay, so what is the producer code? You can see the step number 1, you produce item. So you can see, right? So you can, producer code is what? You produce item. Then so down on empty. Let me take, so empty value, suppose 100 assumption. Okay, down on empty, this becomes 99, and mutex also there, right? Mutex value inside what? 1 down 0, right? Step number 1, step number 2, step number 3, right? Produce item, down on empty, down on mutex, yes. Then you can place the information buffer. Suppose buffer is there, assumption I am taking here. So this is a buffer. Okay, 0 location, 0 1 2 3, like this, 99, total elements, total locations are 100 assumption. Okay, suppose I am placing item name is X assumption. Okay, then what is the fourth statement? Fourth is placed, and fifth is what? Increment in variable. So like n equal to initial is 0, so 0 becomes 1. Okay, then full also there, right? Full initial is 0, okay, then we are making to what? 1, correct? We are making to 1 or not? You can go and see. Producer code. Down mutex, place item the buffer, incremented in up mutex 5, 6, 7, okay. So this 5, 6, 7, okay. Now see what happens now. So once, so one up, when you write up full, what happens? This override again will repeat or not? Again it can repeat or not? So when you repeat again, so what happens, you know, up full when I write it, what does meaning? What does up operation performs? You should, if blocked process is there, you have to wake up or increment full, like no, you have to full equal to what? Initial is 0, it becomes 1, right? It becomes 1, and control may pass to what? Consumer. Control is passed to what? Consumer. Suppose a consumer comes, let's take a time t10, consumer comes. What is step number 1 consumer ko? For consumer, so down on full, right? Down on full only there. 1 is there, 1 down 0 successful. So I can go on second statement. Down on mutex, because already mutex is performed 1 only, right? In a producer code, you see up mutex means mutex value already 1. So now, so I am performing down on full, down on mutex, take the item from the buffer, third one. So I take the item from the buffer, third one, and fourth one what? Decrement. So increment out equal, out value 0, 0 to 1 it became. And what is the fifth statement? Up mutex. So mutex becomes 0, now becoming what? Again from the consumer point of. And 6 what? What is 6? Up empty value. Empty value becomes what now? 100. It becomes 100 or not? Now seventh one, you consume the item. Okay. Now suppose consumer started assumption. So consumer going to be blocked or not now? Suppose consumer only continued, because while one continuously running, right? If consumer started, what happens here? First code down on full. So full value already 0, 0 down minus 1. It is going to be blocked. Ultimately producer will start. Producer will place the item, and it can wake up the consumer block process. So this way, you know, they run the cooperatively. So definitely there is no any inconsistency between the what producer and consumer during their execution. So this way solution given by the semaphore. And one challenge can occur here. Okay, one challenge can occur. One challenge can occur. So during this semaphore operations, let's look at the producer code assumption. Let's look at the producer code. Okay, as well as the consumer code. You observe consumer code. Okay, consumer code. What is the statement number? Like statement number 2 here, producer code. Just you might have copied. So down. Okay, down on empty. Correct on down on empty. And third statement is what? Down on mutex. Down on mutex. Here what is the first statement in this one? Down on full. Down on full. What is second statement? Down on mutex. Down on mutex. Down on mutex. These all operations once you can confirm in producer code. Down on MP, down on mutex is there. In consumer code, down on full, down on mutex is there. Suppose, so as a human you understand, sometimes we do errors also, right in the code. Anyway, it perform the down operation. Here also down followed by down is there. Suppose by mistake, suppose it is interchange. This is interchange assumption. These two also interchange in a consumer. These two also interchange in the consumer code. What happens? We'll see. So this analysis part we will see. So analysis. Okay. So now ready queue, two process available, producer comma consumer. At time t0, assume sir, consumer only scheduled first assumption. Consumer is scheduled first. Okay. In consumer code, what I am saying? So in place of 1, 2 is there. In place of 2, 1 is there, like this. Reverse. These statements are reversed. Okay. First statement is down on full only, right? So I'm taking, you know, empty value. Empty equal to 100 slots are there. Full equal to 0 is there, and mutex equal to what? 1 is there. Okay. First operation. What is first operation? Down on full. So down on full only, right? So sorry, it becomes the reverse, right? Down on mutex. So down on mutex 0 successful. 1 down 0 successful. Suppose if for a second statement, I repeat what I am trying to do in consumer code. If these two statements are reversed, like no swapped, and producer code, these two statements are swapped. What happens we are seeing. Okay. So, first statement mutex 1 down 0 successful. The second statement is what? So, down on full only. So, down on full. What is full value? 0. 0 becomes -1 counting semaphore. Now, what happened? Unsuccessful operation means what? Consumer going to be blocked, correct or not? Blocked. Then at time t2 producer comes, it will run the first statement. First statement is a produce item. Then what second statement is? We have exchange, right? This we exchange. Second is what? Down on mutex. What is the mutex value now? 0. 0 down, 0 only. So, this is also going to be blocked or not? So, this also blocked. So, both the process blocked. This indication what? Both the process blocked. No process not going to be executed, right? So, deadlock happens. Deadlock happen. So, now see, it is initially producer consumer problem was having the inconsistency. Through semaphores we resolved it. But through semaphore, another big problem can create deadlock. So, deadlock always will not happen. Deadlock always will not occur. By mistake, this statement reverse. This statement reverse, and consumer started first execution. Consumer started first execution, performing down on mutex 1 down 0, then full down on full 0 -1. So, it's blocked. This also get blocked. So, what is the conclusion? When multiple semaphore operations are used in the application, the programmer must ensure proper order of usage of the semaphore operations. If the order of semaphore operations are not proper, definitely another problem, that is deadlock, can happen. So, this is observation from this this topic. I hope you understand the implementation of the producer consumer problem with the semaphores. So, the code is given, you can go back and watch and copy the code and understand yourself. So, in this like producer consumer based in a gate exam, previous year gate exam, I think couple of times they have framed the question. They given as it is a code, some mistakes or some kind of observation they made in the statement wise, you have to choose it. If you understand well this statement, this code and analysis part, definitely that type of questions you are able to solve it now. So, now I would like to stop the session and I want to continue semaphore part 3, in which I would like to discuss reader writer problem, like semaphore based solution for reader writer problem, the second classical IPC problem, and also we will see some problems like the previous year gate questions or other types of questions, how they can frame on the semaphore entire concepts. So, those part I would like to discuss in part 3, so that the entire topic will be together. So, definitely this is going to be beneficial for you, and the gate examination point of view, understand from IPC synchronization, semaphore is much important. We can expect 2 or 3 marks questions we can expect from this area. So, also I am like suggesting you can also visit the visit the website. You can observe what IMS is going to provide it. More than 800 hours of the live classes, so physical classes or online classes we are providing, and apart from this 30 plus theory books, exercise books, as well as so more than our last 33 and 34 years previous year gate questions, and with alternate solutions, important observations, with the video solutions provided by the IMS Gate Academy. And apart from this, there are 12 my plan sessions, personalized my plan sessions, to getting the better guidance for the students will be getting. And apart from this, more than 130 tests. So, various tests you understand, chapter wise, subject wise, multi subject, various mock tests, all are provided by IMS. So, you can definitely, if you are willing to take the admission, so you can book the free counseling to get the better information from this. So, like apart from this, you can join the our Telegram group to getting important updates related to GATE exam or other PSUs, important information. And also you can get the free content like the YouTube schedules, like all the free classes of YouTube schedules, and the YouTube classes PDFs also will be getting in this Telegram. Apart from this, understand our experts, like all the faculties, we are keep on posting the quiz questions daily basis. So, that definitely really boost your preparation, like getting the clarity over your conceptual things by solving the daily questions. So, these are the things you can get it from this Telegram. You can join the Telegram. Thank you so much all. Definitely this session is going to help you a lot, and so also try to subscribe the channel so that future all the videos will be getting notification, because the semaphore I would like to continue into part 3 also, in which I will discuss the rest of the part. Thank you so much all.